are you?
Good. Let me open one of my drawing tablets here.
Okay.
All right. So what do we got today?
Okay. Let's see. Okay, so I have find vertical asymptotes and describe the behavior of f of x to the left and right of each vertical asymptote. And then f of x is x over x minus 2.
Okay. Let's start with vertical asymptotes.
Mm-hmm.
What are they? Vertical asymptotes are always what makes the denominator 0.
Okay.
So what makes this denominator 0?
Do you have to add something to the top, or is it just...
No. Just take the denominator, set it equal to 0, and solve it.
Oh, okay. So 2.
X equal 2 makes the denominator 0. And that's the vertical asymptote. So the next step in graphing this thing is to draw the vertical asymptote. Now, they want the behavior on either side of the vertical asymptote, which means we kind of need to draw the graph. What's the horizontal asymptote?
Isn't it whatever cancels?
No, if the degree of the numerator is the same as the maximum degree of the denominator, it's the ratio of their coefficients.
So just 1?
Uh-huh.
Okay.
So there's our grid that we're going to draw this on. That's 1 and that's 2. Now, there's two possibilities for a hyperbolic function. Either it's going to look like this, or it's going to look like this. So let's figure out which one it is. How can we do that? In other words, let's assume that it's this one, first and third quadrant. How can we verify that?
You could plug in a point, right?
Well, plug in what point?
Something on the x, so like 3.
Good. In other words, you want to go probably to the right of that vertical asymptote. So when you plug in 3, what do you get?
3 over 1.
All
so
right.
just 3.
So when I plug in 3, I'm at that point right there, which would indicate that I've drawn it correctly. In other words, I'm indeed in the first and the third quadrant. Had I gotten a number less than 1, then I knew I would be down there like that. But I didn't. In other words, I now know that this is the correct graph. Okay. Now, let's examine the behavior of this thing as we approach the vertical asymptote from the left and the right.
Okay.
What happens to the function as I approach 2 from the left? In other words, what is the limit of that as x approaches 2 from the left?
It goes to negative infinity.
Exactly. What happens to it as I approach 2 from the right?
And then that would be positive infinity.
Okay. What's the limit at 2?
It wouldn't exist because they're not the same.
Correct. Correct. You got everything about that right.
Okay.
And just always know that when you're looking at a rational function like that, it's almost always hyperbolic in nature. Hyperbolic meaning that it's a hyperbolic function. Just like when you studied conic sections, you had hyperbolic functions that looked like that, right? Or even hyperbolic functions that looked like that. Well, this is rotated at 45 degrees, still a hyperbolic function. And it's asymptotic with that grid, the dotted grid line. All right, what else you got?
Okay, so use graphs and tables to find the limit as x approaches infinity and x approaches negative infinity, and identify any horizontal asymptotes. And then I have x over the square root of x squared plus 2.
All right. We can't take the square root of x squared plus 2.
Right.
But we can see that for all large x, that's the same thing as the square root of x squared, which is x. Which means we're basically looking at x over x. Remember, everything else that comes after does not matter. The only thing you care about is the highest degree of polynomial. And in this case, it's x to the 1 in the top, and it's basically x to the 1 in the bottom, because the square root of x squared is x.
Okay.
Okay. Are there any vertical asymptotes?
No.
No, because you cannot make that denominator equal 0. X squared is always positive, and I'm adding a positive 2 to it. There's no way to make it 0. So no, there are no vertical asymptotes. How about horizontal asymptotes?
Would that just be 1?
Y equal 1.
Y equals 1.
Remember, it's the equation of a line.
Okay.
And that's it. Okay? Now, as x goes to infinity, the definition of horizontal asymptote is what happens to y as x goes to infinity. So we know at infinity that it's going to approach that line. I don't know necessarily whether it's going to approach it from above 1 or below 1, but it's going to approach that line. And the same thing on this end. This end maybe approaches it like that. No, let's see. They wanted the limit as x approaches infinity. Well, what is that answer? Looking at my graph. Look at my graph.
Would that be 1?
What about when x approaches negative infinity?
That's also 1?
Yeah, because negative infinity is really no different than positive infinity if you plug it in.
Right.
Negative squared is a positive, so we might as well, in other words, once we come up with that answer, it's got to be the same for the other side.
Okay.
So that's what it is. You end up approaching a horizontal asymptote as x goes to infinity, or in this case, negative infinity also. And this is, you have to make this leap in knowing that the only important part of that expression is the square root of x squared. We do not care about the 2. In other words, if I gave you something like this, x cubed minus x minus 100, and it's all divided by x cubed plus 1000x minus 1,000,000, none of these matter. Only
Okay.
thing that matters is the ratio of those coefficients, which would be 1 over 1.
Okay.
Okay? Well, you can apply that logic to this kind of a problem, in that the only thing, I don't really care about this plus 2,
Mm-hmm.
and if I cross it out, now the square root of x squared is x, so
Mm-hmm.
the highest exponent in the denominator is really 1, and the highest exponent in the numerator is 1. They're equal, therefore it's the ratio of those coefficients.
Okay. Okay, so, let's see. Oh, I'm a little confused on like the fraction problem, so
Yeah, I was just going to suggest, isn't that where we ended?
yeah, I
Yeah,
wasn't
we did.
really too stable on that.
Yeah, I felt like we should put some more effort in that.
Okay.
Seemed exactly clear on that, so.
Yeah. Let's see. I have limit x approaches 0, and then 1 over 3 minus x minus 1/3, and then all over x.
Clearly, if we substitute, we get 1/3 minus 1/3, which is 0 over 0.
Mm-hmm.
So that doesn't yield any answer. It's indeterminable.
Mm-hmm.
Well, we have to perform this operation. This is not a limit problem that we're going to solve by factoring.
Okay.
We have to be able to do this. 1 over 3 minus x minus 1/3. How do you do that problem?
Do a common denominator.
What is it? Don't distribute it. Just multiply the two terms.
Oh, okay. So just 3 times 3 minus x.
Yeah, that's always a common denominator. It isn't always the least common denominator, but we really don't care whether it's the least or not. What's this?
Would that just be 3?
Yeah. What's this?
3 minus x.
Now, are those the two same fractions that we started with?
Yes.
And that's very important to check. Okay? And I added parentheses there because I had to. In other words, I'm subtracting 1/3, so I'm really subtracting that whole quantity right there.
Yeah.
That's why you need the parentheses in the numerator, is that this quantity is 1/3. Okay? And if I don't add the parentheses, I'm going to have some serious problems, because now simplify that. And remember, this is all over x. So I still have an x in the denominator. I just haven't, let me move it a little bit lower. So this is the numerator.
So
that's the common denominator.
Yeah.
Simplify the numerator of the numerator.
So that would be 3 minus x.
It's 3 minus 3 plus x.
Plus x, okay.
See why? This negative sign has to be distributed to both terms.
Oh, okay.
So you do have 3 minus 3 minus a negative x. So those two cancel, but the minus minus x turns into a plus x.
Okay, so that's why you need the parentheses?
Yes. If I didn't put the parentheses, and this is an unusual problem in that it's not that often where you have to actually add parentheses, or you get the problem wrong.
Right.
Usually they're there, and it's a question of whether you distribute or not. But in this case, you actually have to add them.
Okay.
Now, let's look at this. we have x over 3 times 3 minus x all over x. Now, the rule is if you are dividing by a fraction, you flip and multiply.
Okay.
Well, we're not really dividing by a fraction, we're dividing by x.
Mm-hmm.
That doesn't mean we can't put a 1 under it and flip and multiply. We can.
Okay.
Okay? So, if I multiply, I'm going to multiply by 1 over x, right?
Mm-hmm.
In other words, that's the same thing as what you see in the upper right.
Okay.
Now, those magically cancel, and we get 1 over 3 times 3 minus x. And there's no need to ever distribute that. What's the limit of that as x goes to?
So 1 over 3 times 3, so 1/9.
Yeah, as x goes to 0 equals 1/9.
Okay.
Okay, so the
Mm-hmm.
whole secret of this is being able to handle complicated looking fractions.
Yeah.
In other words, if I said, what is 1 over x minus 1 minus 1, now let's make it 2 over x plus 3. How do you do that operation?
So common denominator.
Okay.
So
What?
you would multiply, so x squared.
Don't always leave it in factored form.
Oh, okay.
Don't waste the time to multiply it out, because you
Okay.
see that it's wasted time. You're not going to need it multiplied out.
Okay.
Okay, so it's just what?
So just x minus 1 times x plus 3.
Right. Now what goes in the numerator of this one?
That would be x plus 3.
Right. And I'm going to put parentheses around it just because it's safer.
Mm-hmm.
Excess parentheses never hurt you. Leaving them out can often hurt you. What goes in this numerator?
Would that just be 2 times x minus 1?
Yeah. In other words, as long as that's the same thing, that's what it is. And that's what
Okay.
you always have to do. You always have to make sure that that is the same as that, and it is. And you have to make sure that is the same as that, and it is.
Okay.
Now, what's the next step?
Can you cancel or?
No, not yet.
No?
After you have gone to all the trouble to get a common denominator, then you need to simplify the numerator. In
Okay.
other words, this answer has a common denominator of x minus 1 times x plus 3.
Oh, okay.
What's its new numerator? In other words, now I can operate on that. Because they have both the same denominator, what's the answer to the numerator? And to do this one, you do need to distribute that.
Oh, okay. So negative, that would be negative 2x plus 1. And then would you subtract the x
Well,
plus 3 from that?
let's start from the left.
Okay.
Remove all parentheses from the top.
Okay.
The parentheses on the left weren't needed to begin with. I only added them for clarification.
Right.
Now what?
So just x plus 3 minus
Fun. X plus 3 minus what? What's the result of this?
2x.
Okay, that goes there.
And then plus 2.
Correct. Now I've removed all the parentheses, and I can simplify. What's the top become?
So x, negative x, and then plus 5.
That's the answer. So that's how you add and subtract complicated fractions like that.
Okay.
And it's not always a 1 in the numerator. That's why I put a 2 here. Sometimes you have to multiply by that 2.
Yeah.
But that's the answer. And that's as simplified as I can get, in fact.
Yeah.
Okay.
Okay.
Got about 5 minutes if you have a 5-minute problem.
Okay. Okay. Alright, so 3 plus x squared minus 9 all over x, and then the limit x is approaching 0.
Again, we have 0 over 0 with direct substitution. Probably, since we're squaring it, the easiest way to do this is just to go ahead and square that, and then we'll simplify the numerator. You'll see what happens. In other words, we also happen to be looking at difference of perfect squares here.
Yeah.
So you could take a more sophisticated approach, but it's hardly worth the effort because it's not that hard to square 3 plus x. Go ahead and square 3 plus x.
So that would just be x plus 9. Well,
no, start
x
with the
squared.
3. Remember, what you're doing is this. And do it in order. In other words, you don't always have to have the x in front.
Oh, okay.
That's what you're doing.
So,
Boil those two.
9 plus 3x plus 3x
Just plus
6x. Yeah. And then plus x squared.
Okay. Then I'm still subtracting 9. I'm still dividing by x. Okay. And this always happens where anything that doesn't have an x term goes away. In other words, the 9 cancels with that 9, and we're left with 6x plus x squared all over x. Now what can you do? In other words, we still have 0 over 0, but we're not done. Now for factoring.
Can't you, so that would be x.
Most limit problems, you should always be thinking factoring.
Okay.
There's a few where we had that fraction, 1 over 3 minus x, which was not really a factoring problem. But most of them are.
Okay, so you would take out an x from the top, and then it would be x plus 6, and then all over x. And then the x's would cancel, and then it would just be x plus 0, which would just be 6. I mean 6 plus 0, which would just be 6.
Right.
Okay.
Okay. And so all of these pretty much are the same thing. In other words, all of the ones that are 0 over 0, by the time you expand, factor, cancel, you're going to get an expression that no longer becomes 0 over 0. It turns into a number. And that's really the secret to 80% of them. Now, there's only 2 other kinds of problems, and that's ones involving that in some shape or form, and one involving where you have fractions like that. Now, these are not factoring problems. These are, you got to go ahead and perform that operation.
Yeah.
You have to know the algebra to do that, and you have to know that one is equal to 1. So even if you have something like sine squared of x over x, you can separate that. That actually is a factoring problem because it becomes sine of x times sine of x over x, and that's 1. but that's 0. Em, I gotta go.
Okay.
Talk to you later.
Yep, thank you.
Bye-bye.
Bye.
Hello. Yeah, hi, Joe. Well, I'm good. I'm in the middle of a session here. I'm just finishing one and starting another one. No problem.